Hi everybody, this lesson is about energy conservation and vertical circular motion. Okay, so let's just take the roller coaster as an example, and this part of the roller coaster is called loop the loop. So I'll just write that down. So this is called loop the loop. Okay, so before you actually do this loop, what happens is if you go to one of these fun parks, theme rides, roller coaster rides, your cart is going to be taken up a really high hill. And you'll notice that this hill is much higher than that. And there is a reason for that. Okay, so let's just discuss the energy changes. So when you're at the top of over here, and if you're motionless for just a little bit of time before you come hurtling down, all your energy over here is gravitational potential energy, where capital H is the height of this hill, m is your mass, and g is acceleration due to gravity. When you come down the hill, and let's assume that no energy is lost in the form of friction, in reality it is, but let's just take ideal conditions over here. So all the energy will be kinetic, and that's equal to EK equals half mv squared. So if I just put some numbers here, and if there's 100 joules of energy at the top here and no energy is lost due to friction, there will be 100 joules of energy over here, and there'll be 100 joules of energy no matter where it is in this whole motion. Okay, and then let's look at this part. When you're kind of going upside down on the loop, you still have 100 joules of energy, assuming it's 100 joules, but not all of it is gravitational potential, not all of it is kinetic. It's a combination of the two. So over here, you have some gravitational potential energy and the remaining is kinetic. And the amount of gravitational potential energy here is not going to be as much as at the top there, because this was much higher. And this is because you are moving and you're at a height. That is why you have these two forms of energy. Let's just try and find out what is the relationship between this radius of the loop. In reality, it's not a perfect circle, but for us, let's just assume that's a circle. Okay, what's the connection between this radius and that height? And to do that, there are lots and lots of ways of solving it, but one way of doing this is to look at energy considerations. Okay, so at the top, yes, I'm just going to rub out this bit. Okay, we're just comparing those two, or maybe I just make that a little one. Okay, so that's your radius. Okay, so at the top here, all the energy is gravitational potential, which is equal to mgh over there, and all that energy is converted to these two forms over here. And over here, the gravitational potential energy is mg. It's not as high. You're okay if I say this height is twice radius, because that's your radius plus another radius gives you the diameter. So times 2r plus kinetic energy is given by half mv squared. Now we just learned that at minimum speed, when you feel weightless, this v squared is actually equal to rg. So in place of v squared, I'm just going to put rg. So now let's just look at all the terms in this equation. You find that m and g are common factors in all these terms. So what are we left with? We are just left with h is equal to twice r plus half r, or the height of the high hill. 2 plus half is 2.5. 2.5 times radius. So that's a connection between this radius and the height of the high hill. So this one, if this radius was 10 meters, this will have to be 10 times 2.5, which is 25 meters high, for you to be safe and carry on. Okay, in reality, they might be much bigger. Okay, so you do faster speeds over there. I hope that helped. Bye for now.